In this video, we show how to produce the graph shown in figure 5.9 on page 193. We follow the instructions given in example 5.7a on page 215. First, open a one-dimensional form. Plot a graph. Load this formula here. It says to use 8192 points on 0, 1. So 0, 1, 8192 points. Click plot. And there's a graph of the signal. If we connect it by line segments, we get that. Ooh. There's a lot of oscillation going on in the various regions there. This is actually the figure drawn in the book. Now we transform Fourier and click this option here, 0L to minus AA. Click plot. And there's a graph that shows real and imaginary spikes here. We're locating the frequencies, but there's with this representation there's very little information you can see about where the time that these frequencies are being taken on. It is there, but it's hidden deeply in the relationship between the real and imaginary parts of that transform. Let's look instead at a spectrogram, which is under the analysis menu of Fawav. Spectrogram. And we'll just compute here. And there's a Blackman windowed spectrogram, which, as one can see, very clearly locates the time positions where the various frequencies, which are, this is the frequency axis here, and you can examine the figure at your leisure in the text and see that the position of these line segments here, the dark parts correspond to the frequencies of the sines and cosines in that test signal, and we've fairly accurately located the time positions where those frequencies are prominent. Now, Blackman windowed spectrogram is a very commonly used one, and the book contrasts that with a rectangular window or boxcar window, which does not introduce a window function like the Blackman, and greatly distorts the signal. This choice is here just for illustrative purposes. We can see it's a terrible looking spectrogram. The windowing by the Blackman window greatly improves the appearance of the spectrogram. That concludes this video. Thank you for watching.